I guess I met you and you've met me before. My name's Jay Kunz. I've been here for about 14 years. I was dean for 11 years, tried to retire and it didn't work, so I came back to see how it would go. With all of you folks, nuclear is very exciting, and of course we're going to focus on nuclear, but my focus in this morning's talk will be on energy in general, because that covers everything. That covers electrical, civil, mechanical, computer science, as well as nuclear. So we're going to touch on all that. But first, I would just like to go over a couple of things that other people have talked to you in the past about. And a question that came up, and it was from somebody who was sitting right back there, but I don't know if I see you did. Who asked about cancer treatment last time? Nobody. He was sitting right back there. Okay. Let's review with you some of the things that Dr. Dunzig-Geiger talked to you about. If we can go to the Elmo. We get background radiation, just natural stuff. It comes from cosmic rays, and it comes from the cement here. It comes from bricks. Radiation comes from the ground, and it's about 160 milli. Rem, I'm just going to call it an R, whether it's a rad or a rem. They're all about the same thing. That's per year. If you live in the USA in a standard home, like we have, it's estimated you get an extra 200 of these from radon, gas that seeps up through the ground into your basement. It's an inert gas like helium, so it doesn't combine with anything. It just gets into your basement, and that decays. And if you happen to breathe it in and it decays while it's in your lungs, then there's some solid particles in your lungs that are very damaging to the lungs. And so it's estimated you get another 2. And then just this year, the medical people estimated that medical imaging, now I'm not talking about cancer treatment, like x-rays, CTs, adds another, let's see, that comes to 360, adds another 260, for a total of 620. Okay, that's over a year. Some people in the world live at places that get a lot more. This is background radiation at Idaho Falls and Pocatello. People down near sea level get a lot less. We're closer to the sun, we get more cosmic rays. So down near sea level, I think that number is about 120. And if you're a pilot that flies transcontinental flights or across the U.S., across the oceans, and you have a regular schedule, you're probably getting an extra 500 to 1,000 a year. And if you live in some places where there are high radiation levels in the ground, you can get twice this, okay, 2-3 times that. The Nuclear Regulatory Commission says, and I've said this for years, they've said that those of us that work in the nuclear industry, like some of you will be doing, 5 rads per year maximum additional from your work. But then they have a thing called LARA, as low as reasonably achievable, and they said, hey, you folks working in the nuclear industry, you're supposed to keep your dose down to a minimum. Don't get anywhere close to that, as low as reasonably achievable. So at ISU, guess what? We set the limit of, this is 5 rads or 5,000. Let's get all these numbers consistent per year. Okay. So at ISU, we say 100 millirem per year. Once you get 100 on your film badge, which I didn't bring with me, but once you get 100 on your film badge, then the technical safety officer comes over and meets with you and says, what's going on? What are you doing? Why are you getting so much radiation? They won't send you to jail or to see faculty center or anything like that, but just say, now be careful the rest of the year. If you're working at up in the Health Professions College where they teach radiology technicians, this is a 4-year course, radiology technician course. They allow them to get 625, what as per year, because there's just no way they can keep them down to 100. Okay, another thing that Dr. Mary Lou Dunsig-Gallagher talked to you about, I believe she said that, okay, what's it take to really be fatal to you? And the numbers are like 350,000 millirads or 350 rads in one dose. I think they could call it over 60-day period. That's not one dose, but over 60 days. They just spread it out. There's a 50% chance of dying. Now, the person asked the questions last time, going for cancer treatment, radiation therapy for cancer treatment, and they try to give you 5,000 rads, okay? 5,000 rads for cancer treatment, at least, sometimes more. But they usually give this to you over 20 days, 4 weeks, 5 days a week for 20 days. So it's 250 a day. And it's aimed at the cancer, so 250 a day, yeah, that's not quite that much, but the next day you're going to get another 250 next day. And it's focused on the cancer. Now, you can't focus gamma rays, but what you can do is you can move the machine around the patient. So if the cancer is here in the stomach, shoot first at the stomach from the front, and then from the side, and then from the other side, and then from the back. And that spares the healthy tissues around the stomach, but does focus the beam. Each one of those beams goes right at the cancer in the stomach. So that's how they treat that. Okay? Any questions or comments about that? Next thing I'd like to do is just reiterate, because I think you've been talked about this before. I'm going to do it twice today. Okay? Last time, Dr. Mary Lou Dunsig-Gallagher said, think about the nucleus and think about the electrons going around it. Now, she had a nice analogy, which I hadn't heard people using before. I usually use the analogy, the comparison in distances and sizes is like the sun versus Pluto out here. And there's a lot of empty space, solar system. What she gave you was, she said, okay, put a P, and this is the goalpost out here. This is 50-yard line. That's pretty close to being realistic. Now, there's one other thing about it. Don't make this a P, but make this a ball bearing. And that doesn't even do it. You have to go to a steel ball. To have the right size, it should be a ball bearing. But to have the right weight, it needs to be steel as big as a softball. And these little electrons floating around out here have to be like milkweed seeds. So the relative mass is like a pea that has the mass of a softball made of steel or lead. And these little electrons floating around out here are milkweed seeds. Now, all these years, civilization's been on the earth. Fire, then along came gunpowder, then along came TNT, and then along came gasoline engines and cars. All these years, we've been playing with the electrons, chemical reactions. We just fool around with the electrons and have them react one chemical with another. Burn gasoline with oxygen in the air, and so forth. Never knew about this. Never knew about this until, really until Hahn and Strassmann. Oh, they knew a nucleus was there in 1913. But then Hahn and Strassmann did some experiments in which they concluded that they'd split this nucleus. And the difference was fantastic. I'm not talking about the difference. Yeah, a Toyota Prius gets twice the gas mileage that a Ford Mercury Grand Marquis or Ford Victoria, whatever it's called. Yeah, factor 2 gas mileage. Yeah, that's neat. That's pretty neat. And when you talk about, okay, how much does coal add to the cost of our electricity? Well, the cost of the coal amounts to about 20% of the cost of our electricity. And you say, hey, if we could cut that, if we cut that 20% off, by using solar. Hey, look at the gain we have. I'm not talking about 20%, 50%, or factors of 2. I'm talking about factors of 4 electron volts for these reactions, like carbon plus O2 goes to CO2, or H2 plus 1/2 of an O2 goes to H2O. We're talking about 4 eV for one of those. Split that nucleus, and we're talking about 200 million eV. Now, when this was discovered, and scientists all over the world came to this realization, if you'd been a scientist in those days, you would have said, I can't believe it, and yet it was proven in the United States in 100 universities within a year after this discovery was made in Germany in 1938. At least 100 universities repeated the experiment and showed, yes, this is it. Now, you know, this is a factor of over 1 million. What is it? This is 50 million, right? It's not a factor of 2, folks. It's 50 million. And you see this and you say, that's what nuclear is? Let's do something with it. Now, the unfortunate thing is, in 1939, Hitler invaded Poland and started running all over Europe, and this was discovered in Nazi Germany. And scientists said, it can make a darn good bomb, right? And we have to get that bomb before Germany gets it, or we're in tough shape. The whole world's in tough shape. So we had a crash program to build that bomb. And the first thing the public ever knew about it, because the scientists in the United States said, we're going to have secrecy. Okay? We're going to have absolute secrecy on this. We're not going to publish anything. And they didn't. And the first thing any of the public knew in the United States is this thing was dropped on Hiroshima. And it destroyed the whole city. It was just one bomb, about this big. Actually, the real part of the bomb was only about the size of that was a little bigger than a softball. It wasn't quite as big as a basketball, maybe soccer ball size. But the stuff to carry it and put the 2 halves together made it, you know, something you could get your arms around. Pardon?
Didn't they call it the Fat Boy?
The one on Hiroshima was called Little Boy. Okay? The one was exploded in the desert in Alamogordo 3 weeks before that was a Fat Man. Okay? And the one that was dropped on Nagasaki was a Fat Man. Okay? The little boys were made of U-235, and the Fat Men were made of plutonium-239. And practically all our nuclear weapons now are hydrogen bombs, but they have a trigger that consists of the atomic bomb, and they're all plutonium bombs. They got them real skinny now. Okay, they're no longer Fat Men anymore. And in them is a lot of deuterium and tritium, which makes a hydrogen bomb like the sun makes energy. Okay. This is just a difference, and this is why nuclear is so fantastic. After the war, they said, okay, let's start making something peaceful, and nuclear's come a long way. I just asked my students the other day. I said, okay, now every year they discharge fuel from all these 104 nuclear power plants. And I asked them to work this problem. I said the fuel assemblies are 12 feet high, a little higher than the ceiling, and suppose they stacked those on a football field. But they started going the whole width of the football field, which is, 160 feet across, I believe. How many yards would it fill up? How many football fields would it fill up? And when we were through calculating, hey, it'd go from the 0 to the 2-yard line. Really? And these plants have been running for now nearly 50 years, so 2 yards per year, okay. We have enough fuel that would almost fill up a whole football field now in used fuel. We haven't used it up completely. We call it spent fuel. We could reuse it. We've only used 6% of what's in it. So actually it could produce 10 times as much. But we're saying, no, it's so cheap. We just want to get rid of it and store it. And Senator Harry Reid said, not in Nevada. I'm not going to do it there. Okay. Kumar, could we go to the computer? Okay. We're just trying to answer some of these questions. Take a look at that. That's a view from space. Those are lights in space. Where are we? I believe that's Idaho Falls, and that's Pocatello, and that's Blackfoot, and that's Twin Falls, and that's Boise, and this is Salt Lake City and the Wasatch Front. That's Denver. Hey, there's nothing out here really. Just a few of us people. Okay? It's all, oh, there's the world at night. Interesting. You know, where are the lights? And now where are the nuclear power plants? Let's see if we can go nuclear power plants here. Come on. Oh, it takes its time, doesn't it? Well, remember that. Remember that when we get to nuclear power plants. Here's an energy flow chart. I did not update it to 2008. Everything else in this, which will be on Moodle, is updated to 2008, but it's not much different. Ah, yes, it is a little different from 2008. We had a recession, and we cut our gasoline usage from 40 of these quads to 37 in 2008. Here it is for 2008. 37% of our energy, this is total energy, not just electricity, 37% of our energy came from petroleum, 23% from natural gas, almost the same from coal, nuclear, electric. It was total energy. This isn't just electricity now. Hydroelectric, biomass, wind, geothermal. I don't have solar listed there because we can't even see it. We'll look at it a little bit later for electricity. 2/3 of our petroleum is imported. Here's where the energy consumption went. That's just a sort of graph of it. Let's talk about petroleum. Now, all of you have seen these big barrels of oil or grease or fat or whatever. The ones that you see that are around the United States that are, you know, outside restaurants usually hold 55 gallons. That's not the standard barrel. The standard barrel, and remember, the standard barrel is this 42-gallon barrel. That's the standard barrel internationally. Anytime you hear talking about a barrel of oil, it's 42 gallons. Forget the 55. Yeah, if you're sent out to fill a barrel, one of those barrels someday, you know, and your boss says fill it up, you'll know you're putting 50, but forget that. Standard barrel is 42 gallons. Last summer, not this one which just passed, but like 2008, oil hit $140 a barrel. So if you just divide 42 into 140, that comes $3.33 a gallon for the raw material. Refining is this. Taxes in Idaho, transportation, retail markup, that comes to $4.38 a gallon. Okay? That's what it was summer a year ago. Right now, it's actually lower than this. Oil is flirting in the $68, $69 a barrel. But if you just take this number and change that number up there to this for $70 a barrel, you get $4.38 a gallon. Is that what I get? No, I'm sorry. Get $2.71 a gallon. What do you expect today? It's a little cheaper than that. If we get down to $40 a barrel, it's going to get down to this. Okay. This is what we project for the market. This is what the market is projecting in the future. They bid in the future. Hey, I'm going to buy this future trading block for December 2009. You know, if I can buy it at 59 and it stays at $70 a barrel, then come December, I can sell it for $70 a barrel. I'm not an oil man. I just have a piece of paper. And I buy this up and say, hey, you know, 10 million barrels of oil in December 2009. And somebody's going to deliver it to me, but I don't have any place to put it. My backyard won't hold it. But I'm going to sell it to somebody in December 2009. That's the type of trading that goes on. And you can see the other prices there. They're sort of gambling on the price of oil staying down. Okay, petroleum flow. This is what we produced. This is what we import. Okay, we're importing 2/3 of the oil we use. Now you say, United States, can't you do better than that? Guess what? Saudi Arabia is the biggest oil producer in the world. Russia's right behind them. And we, the United States, is right behind Russia. We're the 3rd largest producer, and there isn't anybody else close. Iran sort of comes in there, half of what we produce, in 4th place. So it's not that we're shirking our duties. We're doing great. We're number 3rd. And guess what? We have exhausted our oil. I wonder if I have this number in there. We're importing 2/3 of 7 billion barrels a year. 7 billion barrels a year is what we use. 2/3 that's being imported. We identify underground 21 billion barrels of resources that we know exist. Now there's more there, but we don't know for sure where it is or how much it is. Now if you take 7 and divide it into 21, that's 3 years, right? We have identified enough oil to last us 3 years if we didn't import 2/3 of it. Now that is really scary. You know, if we weren't getting this oil from our biggest suppliers, Canada, fortunately, our good friends up north, and I think Mexico comes in 3rd or 4th, good friends down south. But if we weren't getting this 2/3, it only lasts 3 years. But even considering that we still can get this, we have only enough to last us 3 times longer than 3 years or 9 years. Well, this number doesn't keep going down real fast because we have 1,000 drill rigs out there drilling for oil, and they manage to find a little more every year. So this only drops maybe 1 billion barrels a year. So we're doing a pretty good job. And you say, that doesn't sound very good. Hey folks, we have nearly exhausted what we have found underground. We have 600,000 wells, and we're producing 10% of the oil is produced in the world. The rest of the world, from producing 90%, does it with 150,000 wells. 600,000 wells we have. We're dragging everything we can out of that. We're using all sorts of extra efforts to recover the oil. We're squirting carbon dioxide down into other wells and trying to push the oil into the producing well. All sorts of things to increase this. The whole world has about 1,000 billion barrels, the whole world in reserves, in identified resources. 30 billion barrels a year, so 30 into that is what, about 34? So there's enough oil to last 34 years based on what we know exists. But they'll keep discovering more at the time. Natural gas reserves that we have, about 10 times our annual usage. The world's natural gas reserves are about 60 times. So we're better off with gas, but that's a little questionable. And the world's looking pretty good with gas, but hey, most of you are going to live to be 100. So, you know, you're going to go past that. So we have some things to worry about. Here's the electricity flow. Coal produces this. Oops, let's get up here. Coal is about 48%, 49% natural gas, nuclear, renewables. This is what has been generated. This is what we throw away as waste heat. I'm sorry, we can't do anything about that, folks. Those are the laws of thermodynamics. This is waste heat thrown away at about 115 degrees Fahrenheit. It's thrown away in the condensers, and it just goes out. We can't do anything with it. Yeah, you could heat some houses with 115 degrees water, but you'd have to build an awful lot of houses near those nuclear plants to make use of this. Awful lot of houses. And building all those pipelines would just be too expensive. It just isn't worth it. People haven't really found a use for it. Yeah, some people could build greenhouses nearby, and most nuclear plants would say, okay, we'll ship you some of our warm water if you want to keep your greenhouse going, and we'll make a good deal with you, but that hasn't become a big thing either. So this is what we generate, and let's see where we get it from. Almost half from coal, and that's grown about 2% growth in the last 3 years. About 20% from nuclear. It's been approximately constant because we haven't built any new plants for almost 30 years now. Natural gas a little bit ahead. It's been growing like crazy the last 5 years. Hydroelectric fluctuates with the weather. In 2007, this was 7%. I suspect that this year, since we had such a good summer in spring, this may be up around 8 or 9%. Petroleum, boy, gasoline petroleum is so expensive that nobody does this unless they really have to. Idaho Power does have some diesel generators up in Salmon, and they still use them. And they say, oh, and in a real hot summer day, we really need them because everybody's turning on their air conditioners, but we won't use them any other time, but we're glad to have them for those occasional hot summer days. Biomass, that's growing. Now this includes ethanol in your gasoline. Practically every gas pump in Pocatello and Idaho Falls has a little sign on it that says This gasoline contains 10% ethanol. And most of it's made from corn. Now some of it's made from other crops. Geothermal, yeah, 1/3%. Wind doubled last year. It now is generating a little over 1% of our electricity. Pretty good. Can't see this. That's 0.019% for solar. 20% growth in 2 years. 20%, another 20%. No, that's going to take a long time to get this up anywhere close to wind. Okay, let's talk about the price. You live in Idaho Falls or you live in Pocatello, and you got pretty cheap electricity. I think Idaho Falls is a little more than 6.5 cents, but here in Pocatello with Idaho Power, we're paying 6.5 cents per kilowatt hour at our home. Now, electricity is sold wholesale. You know, Idaho Power is selling electricity. There are a lot of hydroelectric left over, so they're selling it to California right now. And they bargain with the California utilities on what the price is going to be. Actually, it's a California state that buys it from them, and they distribute it to the utilities. So there's bargaining going on every half hour for selling electricity and what the price is. And on a very hot day, when Idaho Power doesn't have enough, electricity, they have to buy from somewhere else. So they're buying electricity in those days. This is the price nowadays. About 6.5. Look at this. If you remember anything, it's about 6.5 cents per kilowatt hour. Those of you who are on Rocky Mountain Power, outside of Idaho Falls, I think your rates are maybe up in the 8-cent range. So you're a little bit higher. Renewables. You build a windmill and you go to Idaho Power and say, I want to sell this to you. Idaho Power is required by the federal government to buy it from you. Now, they're not real happy to do that because the federal government says, Idaho Power, you have to pay them the highest price of any of your generating facilities. And right now, that highest price is this is wholesale, is 9.1 cents per kilowatt hour. You're getting it for 6.5. So Idaho Power is forced to buy it from those windmill people for 9.1 cents per kilowatt hour. Now, we have a Public Utility Commission which regulates Idaho Power Company. Idaho Falls is not regulated by the Public Utility Commission because you people that live in Idaho Falls own your own company. You're part of the city and it's owned by the city. But here in Pocatello, Idaho Power is a separate company. It has a municipal franchise. It's a monopoly. But the state of Idaho wants to make sure Idaho Power is healthy. And it won't go broke because you turn on your light switch, you want to make sure you have electricity, right? So they want to make sure that Idaho Power gets a fair return on their investment, but they also want to treat you fairly. So they decide that what Idaho Power can charge you. Well, guess what? If Idaho Power is forced to buy this wind at 9.1 cents, what's that going to do to this? They're going to have to raise this as they buy more wind. So Idaho Power isn't losing money on buying the wind. You are. And if anybody in this class lives in Blackfoot, you probably heard the things going on about Wolverine Canyon. And the press said, this is terrible. Wolverine Canyon, if they put those windmills in, they're going to sell the power to California. And I said, great, please sell it to them. Don't make Idaho Power buy it at 9.1 cents. If they want to sell it to California, that's great. We don't want Idaho Power to have to buy it at 9.1 cents because it's going to raise our cost of electricity. The newspapers never mention this. Okay. Global warming, just go down this real fast. This is sort of thing that shows solar radiation comes in and infrared radiation tries to go back out. That's a global cycle for carbon. I want to show you some statistics. There's a lot of debate. Is there global warming? Is there climate change due to carbon dioxide? First of all, let's look at the carbon dioxide in the atmosphere. 1958, 2005 over here, 2004, actually 2006 over here. This is the carbon dioxide content in the air, and this is in parts per million by volume in the air. It goes up and down. Guess what? It's high in the wintertime, and it's low in the summertime whenever the trees are eating up the carbon dioxide to do photosynthesis. And when the trees lose their leaves, it goes up. Comes down in the summer, up in the winter, down in the summer. It's been creeping up. Hey, I know there's suppressed zero. It went from 315 in 1958 to 385 now, or even above that, 390 if we go out here to 2009. So no doubt it's going up. That's the data, folks. This is the spectrum from the sun coming in. And these are absorption radiation. Hey, this is ultraviolet radiation over here, and this is infrared radiation here, and this is a visible spectrum right in this range. This is what's trying to go out. The Earth is hot, the atmosphere is warm. It tries to radiate to space, which is at virtually 0 degree Kelvin, and it tries to do that radiation, but CO2 has an absorption band, and so this is what goes out. CO2 stops it from going out. Here's ozone. A little bit of ozone stops it from going out in the upper atmosphere. Oh yes, H2O, water vapor, clouds, water vapor in the atmosphere, clouds obviously have a considerable effect. The water vapors, oh, and here's ammonia, methane. Here's some more absorption for H2O, but look at that big thing for CO2. Okay, you saw what happened in CO2. You see what it's doing from keeping radiation escaping into space. Hey, use your scientific reasoning. There's obviously a greenhouse effect. No question about it. That's science. Now, is the Earth getting warmer? I don't know. There's the trend over the last 150 years or whatever it is. There's the trend. Yeah, the trend's upward. Now, we didn't have a real warm summer. And you may read some things that says, hey, maybe it hasn't gone up the last year. Is that just a fluke? Well, one of the things we know, there haven't been any sunspots on the sun for the last 2-3 years. And when there's sunspots on the sun puts out more energy, gets to the Earth. So, yeah, maybe the sun isn't giving as much energy. But this has been the trend. Now, are we going into an ice age? It's possible that the trend at this time is to go in an ice age, and maybe we ought to say, let's have as much global warming as we can. But these other effects we don't know about. We do know the science of CO2 and the greenhouse effect. And the big contributions to that are coal-burning power plants and automobiles, trucks, and so forth. They're about equal. Excuse me, in what they do. This is from fossil fuel use. This is from, hey, they're cutting down forests out in the Amazon. This is from deforestation. This is the effect from ammonia, and this is from nitrogen oxides. Let's get through these. Let's just take a look at Idaho. Where do we get our electricity from? Hey, 42% comes from coal, 48% from hydro, natural gas, non-hydro renewables like wind. You know, right now, this is almost 5 years old when they did this study for Idaho. Right now, Idaho Power has 6% of its installed capacity that it can use. They don't own it. It's people they have contracts with. 6% of their installed electric capacity is actually wind. And that's about equal to Texas. So don't take a back seat. All these wind people are saying, come on, Idaho, you're way behind. Texas is doing great. Idaho Power has about the same percentage of wind contracts as the whole state of Texas. Nuclear, hardly anything. It comes from the Columbia Generating Station at Richland, Washington. That's where the Snake River runs into the Columbia. It's the only nuclear plant in the Northwest, and we buy a little bit from that. Now, some of you are going to say, come on, the Idaho legislature says we're not allowed to have any coal plants. They will not give any license for coal. And we don't have any coal generating plants in Idaho. Where do we get this from? Wyoming, Nevada, Oregon. Hey, they have coal plants, and Idaho Power owns a share of all those coal plants that I mentioned, 3 of them in those states. And so they bring in electricity from those coal plants. And I'm glad. Most of it comes from Wyoming. We hope Wyoming never says, oh, come on, we're not going to deliver you any electricity. No, they're not going to do that because they can't use all they're producing by any means. Okay, now I'd like to talk about numbers because in engineering, you need to have some numbers in mind. And just think about, yeah, I can make a graph so you can see the numbers, but you can tell numbers. Three Gorges Dam in China, 18,000 megawatts. Low-head hydro dams in Idaho Falls, there are 4 of them, and they're 6 to 10 megawatts each. Okay. And some of you in Idaho Falls may not have known of these. The one's right down there downtown at the Broadway Bridge. But there's this big Three Gorges Dam in China, 18,000 versus 6 to 10 for each of those little ones. Okay, what about the big ones? American Falls, 108 megawatts. Palisades Dam, 160. That's peanuts compared to this, or compared to Grand Coulee, or compared to the Jim Bridger coal plant in Wyoming near Rock Springs, which Idaho Power owns. 1/3 of it. I think Pacific Power and Light owns the rest. Typical existing nuclear plant, newer nuclear plants. Just keep these numbers in mind. And remember that picture of the United States? There wasn't much. There weren't many lights in the western part of the United States. Sorry, this is a little bit blurred. I apologize. One of the neatest things that people have developed, engineers have developed, you folks, the people that came before you as engineers developed, is the gas turbine combined cycle. It uses natural gas, and I think you've all talked about efficiency of power plants, of thermodynamic engines. Your car engine, your gasoline engine in a car is about 20% efficient. Diesel motors and trucks, they'll approach 30% efficiency when they're cruising along the highway. Nuclear power plants, 34% efficient. Coal plants, 42% efficient. But within the last 4 or 5 years, engineers have made the gas turbine combined cycle 60% efficient. It uses a gas turbine just like a jet engine, discharges it, is connected to a generator, discharges it, and heats steam from that hot discharge, which is about 1,000, 1,100 degrees Fahrenheit heat steam, which goes through a turbine and drives another electric generator, goes through a condenser, comes back, and okay, these things are 60% efficient. They're actually great, but natural gas is not cheap. It's now around $3 per 1,000 cubic feet. It did hit $14 at the peak of the oil crisis. So that's one of the big uncertainties with the great machines. But who knows what the natural gas is going to cost. Boone Pickens, you've heard these ads on the radio. He said, we need to use natural gas. Yeah, he owns lots of gas wells, so naturally he's going to say that. He also says, let's use wind. Okay, and he's right. Hey, we have more gas than we have oil, natural gas than we have oil. And these plants use only 1/3 as much water for cooling the plants as does a nuclear plant. Only 1/3 as much? So guess what? We in Idaho, water's awful scarce. The farmers are fighting over it. You know, it's been a big issue. Just think, what kind of power plant is Idaho Power going to build? Since water is a big deal, they're going to build this long before they even consider a nuclear plant, unless it's somewhere else other than Idaho. They may buy part of a nuclear power plant built somewhere else on the Columbia River, for instance. They might be glad to buy a share in that, but they're not going to build one in Idaho. And the nice thing about gas turbine combined cycles is it only emits 1/3 as much CO2 as does a coal plant. That's another big advantage. So yeah, build natural gas, except you're not sure the price. Idaho Power is planning on building one, and they're telling me their price for electricity from that is 12 cents a kilowatt hour. I'm sort of questioning on that and what they're saying, how they're going to use it. They're sort of going to use it for load following rather than for a base loaded power plant. Load following means, hey, when you don't need the electricity, you're going to shut it off because natural gas is so expensive. But when you do need it, you're going to run it and to follow the load of what's needed on the system. Incidentally, wind has only a 30% capacity factor. I just talked about capacity factor. There are 8,760 hours in a year. If you ran that plant 8,760 hours a year at full output, 100% capacity. If you only ran it at half that many hours in a year, it's 50% capacity factor. If you ran it all year long, 8,760 hours, and only half power, that's still 50% capacity. So it's a combination of that. If there are 200, somebody ask a question? If there are 200 seats on an airplane, and you only fill half of them, that's 50% capacity. Wind, those windmills up outside Idaho Falls are rated at 1.5 megawatts. But they only produce that for the equivalent of 30% of the year. Now, yeah, they're spinning more than 30% of the year, but they're not producing 1.5 megawatts unless the wind is blowing 30, 40 mile an hour or more. So their overall average capacity factor is only 30%. There's a typical nuclear plant that's outside of, that's in the center of Missouri. Inherent advantages of nuclear. Now I'm going to repeat this again. Hey, you burn a carbon atom, you get 4 EV. You fission uranium nucleus, you get 200 million. Okay, so there isn't much uranium in the earth, right, compared to coal? Okay, let's look at it. When you do the calculations, you find there's 50,000 times more nuclear energy than fossil energy in coal, oil, and gas. Uranium and thorium, the nuclear fission elements that can be turned into fissionable things, represent 50,000 times. And that's not 50,000 years, folks. That's 50,000 times as much. And the coal is going to last us, we estimate, 400 or 500 years. So there's enough nuclear there to last us 50,000 times 500 years. Now, disadvantages of nuclear is dangerous waste. I told you what it was. It was 2 yards on a football field for last year. It's very dangerous stuff. You don't want people to get near it. I mean, you get a bad dose of radiation. And it's still generating heat. But we know how to manage it. And it isn't like it's acres and acres of waste. It's 2 yards on a football field, spread the whole width of the football field for 1 year. That's all. We just have to take care of it. That's a no-brainer for engineers, right? We can take care of that. We can shield it. We can protect people. In nuclear power plants, they put it down in a pool that is 40 feet deep, and they stand these up in the pool 40 feet deep, and you can't measure the radiation on the surface of the pool. So, yeah, we can take care of it. There's no question about it. It's no big issue. That's what it was that's what it is now in 2009. There are about 444 around the world. 30 new plants have been announced in the USA. 14% of the world's electricity comes from it. In France, they produce 80%. Let me just tell you a little bit about France, because Charles de Gaulle, who was a general during the Second World War and then became Prime Minister of France, about the late 1960s and the early 1970s, he said, France, we don't have anything. We don't have any coal, we don't have any oil, we don't have any natural gas. We've got a little bit of hydro, hardly any, because there aren't many mountains in France. What are we going to do? And he said, nuclear is the only way to go. So he established a nuclear training academy for engineers, just like the U.S. Military Academy or the Air Force Academy or Annapolis. And it was a prestigious place where engineers who were interested in going to nuclear power could get an appointment. They go there and get trained essentially at the master's level as nuclear engineers. It was great to be able to be an engineer and go into the nuclear business, get trained at that academy. And he started a public relations program with the people in France saying, hey, nuclear, we know how to do it, we know how to handle it, we can do it safely. And if you have a nuclear power plant near your town, it's going to make 800 jobs continuously. You ought to want it. And so the French people want nuclear power. And now they're producing 80% of their electricity in France. Now, their old friends in Germany, where the Greenpeace people are alive and well, say, no, we don't want nuclear power. And Germany has just voted to tear down all their nuclear plants when they reach the end of their licensed life. Most of us are predicting the Germans will come to their senses and they'll change that law before those plants reach the end of their life. And some people have asked some of these Greenpeace people, what are you going to do for electricity? Well, we'll do it with wind. Hey, come on, folks, you're not going to do it with wind. Well, if we don't have enough wind, we'll buy it from France. Okay. Here we have wind power up above Idaho Falls. This is a shot above Idaho Falls. Those of you in Idaho Falls, if you haven't been up there to see those things, they're great. Those things are 250 feet high. I believe the top propeller may only be 220 feet. I forget the exact height, but it's really exciting to go up there and see those, and they're great. And they can do the job if the wind's blowing But if the wind's not blowing, and this is being sold to Idaho Power, I don't know if it is or not, but Idaho Power does have wind. I suspect this is being sold to Idaho Power. When the wind stops, Idaho Power has to make it up. Fortunately, they have a lot of hydroelectric, and all they have to do is raise the gates on the gate into the turbines and get more water going to the turbine, and they can immediately make up for the wind stopping from blowing, and they can easily adjust for this. So that's an advantage Idaho Power has. Other utilities that don't have hydro like Idaho Power, what are they going to do? They've got a real problem because, hey, you got to shut down you don't have to shut down, you have to cut back on your coal plant. And then, when the wind stops, shove the coal to it. Okay, it's going to take a while to get it up to temperature, but shove the coal to it. Come on, half hour we'll have it up to temperature. Whoops, hey, some people are going to have brownouts in this half hour because the wind just stopped. But hey, you want a good business? This is a good business. You buy a windmill, probably going to cost you $2.25 million to have it bought, put in place. The bank probably wants 10% down payment, or thereabouts, what is 12%, whatever that is. Then you take out a mortgage for 8% for 20 years on it. Your initial amortization costs each year are going to be $202,000. You got to pay the bank. Those are your annual payments. Insurance, maintenance, local tax, and so forth. I'm just guessing, $55,000. Idaho Power is paying you 9.1 cents per kilowatt hour and a 30% capacity factor. You're going to make $358,000. And then the federal government's going to give you a 1.9 cent per kilowatt hour subsidy, which we pay for, of course, all of us. That's another $75,000. So the net profit from annual operation is $176,000 on a $250,000 down payment. Hey, folks, that is a good deal. And so that's why all these wind machines are being put in, because it's darn good business, especially because Idaho Power is forced by federal law to pay you this much. And then the federal government gives you an additional 1.9 cents per kilowatt hour. So if you want to get rich, build wind. But I've talked enough about why Idaho Power is not jumping up and down for joy. You sell them wind, because they're paying you 9.1 cents and they're delivering you power at your home at 6.5 cents per kilowatt hour. So something's got to give. Here's summaries. Let's go, just about running out of time. Electricity for automobiles. Okay, at the current price of gasoline, you have 30 mile per gallon car, it's costing you 7.4 cents a mile. Toyota's going to come out with a plug-in hybrid, a plug-in Prius, I understand, in 2010. Now, Prius can go about 5 to 7 miles on its battery in town. The Prius and the Camry and the Ford Fusion and the Ford Escape all are full hybrids. They can run on just electricity at low speed. And so when you're in town and you're at a stoplight, the engine's not running. And you start up from a stoplight and you're doing it on electricity, just like a golf cart. Okay, electric golf cart. But you can only go 5 to 7 miles through town at relatively low speed. Once you get up to 20 mile an hour, you probably have to kick in the gasoline engine so you have enough power to really come up. But if they do put a plug-in Prius and give it a 35 mile range on the batteries and a 6.5 cents per kilowatt hour, it's only costing you 2 cents per mile compared to 7.4 cents per mile on gasoline. So hey, electricity's great. It's cheap if you run on that. Now, if all of us had plug-in Priuses, we'd probably reduce our gasoline consumption by 75%. Gasoline. I'm not talking about trucks, the big through-off trailers on the road and that sort of thing. I'm not talking about that. I'm talking about just gasoline for cars. Now, some people are going to say, yeah, but we'll have to build all sorts of power plants. Sorry, folks, that's not the case. Our power plants are hardly used at night. Remember, we're not working. The factories, not all the factories are running at night. And we only run our power plants at about 48% capacity factor all year round. So the other 52% are really, not all the 52%. Some of it has to be shut down for maintenance, but a big part of the remainder. If we charge these cars at night, no problem. We have twice as much nighttime electricity to charge all of our Priuses, if we all own Priuses in the United States, enough to charge, or Ford Fusion plug-ins. We have enough at night to do it. We have twice as much at night, so we don't have to build any more power plants. This is what happens. This is a power plant, typical power plant. This happens to be one in Missouri, but it dips during the night, peaks during the day, comes back down. Electric utility issues, no brownouts. We're running out of time. I'd like to just go through a couple things. Water is a big problem. But plug-in Priuses are the solution, right? I spent a week or so teaching a nuclear engineering class in China, and I saw these little bikes. That's the battery. They still have a pedal on them, so they can pedal. The battery will take them about 10 miles. So practically every one of the students at that university had these bikes. And there were many, many thousands of them. They take out the battery, take it into their office or into school and charge it, and then they're ready to go home. If they run out of battery, the pedal is still there. Solar, voltaic, power. Here's your problem assignment. I have some factor for, that's supposed to be of, or that's not supposed to be of, that's supposed to be or. The typical, answer the following question. The following question is this: carbon dioxide is a greenhouse gas, factor, fiction, so forth. Answer those. But the problem assignment, 1.5 megawatt windmills. You can put 10 on a square mile. How many windmills would it take to equal one 12,000 megawatt electric nuclear power plant, which runs at 90% capacity factor? This wind is only 30%. So how many windmills? And at 10 per square mile, how many square miles of land area? Compare it to Bannock or Bonneville County land areas. Okay? This will be on Moodle, and so that's the assignment. Any quick questions? No, we're out of time.
When's it due?
A week from now, okay?